Hi everyone, welcome back. Let's get started. So lecture 3, today is sort of the last lecture where we will talk about more theoretical topics on lossless compression, and then next lecture onwards it's mostly be algorithms. So today we will cover 3 topics. The first one is something called Kraft's inequality, which you will see soon. I will explain when we come to it. The second 2 are really sort of the main result of lossless compression, which tells you what is the best possible lossless compression you can do. And so that will be sort of the takeaway. And that's what we will then try to achieve for the next several lectures. Okay, stop me anytime with any questions. So let me talk about SCL. So what is SCL? SCL is Stanford Compression Library. I will show you how it looks. Yep, please.
For partners, can we just post an ad to ask if
Projects? Oh, for homework. Oh, yeah, like a study group sort of thing. Yeah, sure. Yeah. But you have to submit the homeworks individually.
Oh, okay.
Yeah. For the projects, you can do it in groups.
Yeah.
Any other questions?
You can also use Egg to ask any questions, especially if you are stuck in coding for maybe more than 5 minutes, don't know what exact functions to use. Show me talk about it.
Yeah. So as I go through the SCL thing, basically like the aim of this library is to make your life easy, to make it easy to learn things. But sometimes if you are not as familiar with Python or if you're not familiar with like this style of Python or something, it might become an obstacle. We don't want that. So if you get stuck at any point in anything, just reach out ASAP so that we can help. We have tried very hard, learned from last year. So hopefully this year will be a much smoother experience. Okay, so SCL, what is SCL? SCL, Stanford Compression Library. So this started last year, mostly Kedar's initiative. So what you see, like if you want to learn about compression, right? You learn about the theory, you learn about the basic algorithms, but then you go to find some actual implementations. You want to use it in your research, and you suddenly run across like for some of the implementations you find, for some of the algorithms you find Python implementations that are possible to read, but most of the times you just see a C file with like very low level C, sometimes even SIMD and like that sort of very low level code. That's very hard to read for a beginner. So you don't understand anything. And so it like you can't understand the algorithms, how will you use it in the research, right? So the point here was like we want like many basic algorithms are hard to find, and right, efficient implementations are hard for beginners to understand. And just understanding the algorithms like we understand in class, right, that's not enough to actually implement it. So unless you like actually implement it, you will find that there are many gaps in your understanding. So with that aim, we like started writing some common data compression algorithms research implementations, right? Aim is not to be like the most efficient implementation, but something that you can read and understand. Plus the other aim was to have like a framework so that somebody could like modify these, make their own compressors on top of this, that sort of thing. And the last aim was more selfish, like we ourselves wanted to actually implement these, at least if we want to call ourselves data compression researchers, better that we understand some of these in more detail. So with that in mind, let me give you a very quick tour. So this is the course website, which I hope you have seen. You see fall 23 here, right? Don't go to the fall 22 website, right? Use the fall 23 website, bookmark it, so that because on Google sometimes it might lead you to the old website, right? The homework will be on the assignment tab here, homework 1. If you go to logistics and then you go to useful links, the top useful link is Stanford Compression Library. So let's go there. So it's on GitHub. Right. I guess I will just briefly walk through what's in it, right? So basically it implements a bunch of different common algorithms, a lot of which you will study in class, right? And it will be very useful like for your projects, for example, many of the students last year did projects on extending a bunch of these, right? And then you can contribute back to the library. So there are some prefix-free algorithms. There are some other entropy coders, more efficient ones. And there are some external libraries imported here. There is a getting started if you want to install it and so on. This will all be part of the homework, so you will get to do this as part of the homework. Let me just, so that you get a sense of what's in here. So if you go to the SCL, I hope you can see it. Yeah, okay. Right, so there is a utils one, which I will go through very quickly first. So the first thing you will encounter when you start implementing a data compressor is that machines work with bytes, but oftentimes many of these compression algorithms work with bits. So you need various types of utilities to convert from your bit arrays into actual bytes that you will write to the file and so on. And you will run into this in the homework. So this bit array util file has bit width and integer to bit array to integer, random bit array, just a bunch of useful functions. So in the homework, what you will find is we have tried to provide you hints on what functions you should try to use, right? So just look at the homework code, the starter code, and hopefully it helps you. There are a lot of algorithms we saw last time, right? They work with trees. So there are some tree related utils, some miscellaneous stuff, testing. Right, then many algorithms, as you've already seen, work with probability distributions, right? So you want to sort a probability distribution. Last time we read about Shannon codes where you needed some sort of sorting. You want to normalize things, you want to do cumulative distributions. So just this sort of thing, right? A lot of utility stuff. Enough utility. Let me talk about one thing very concrete thing we saw in class. I think it's in compressors. Yeah, so if you remember last time we talked about prefix-free codes, and we saw that to decode them you go through a process where you keep on adding a symbol and then you try to decode it. So this is sort of the structure of many of the functions here. So it's a prefix-free decoder which needs to have a decode block function and an encode block. Oh no, this is just a decoder, so it will have a decode block function. And to decode a block in a loop, the loop you just see on the screen, let me zoom in. While number of bits consumed is less than, basically as long as you have bits left, you try to decode a symbol. And then in a loop, basically you decode one symbol at a time. That's prefix-free decoding. And you might ask how do I decode a symbol? Let's see. Yeah, so here is decoding a symbol. So line 166, you set num bits consumed to 0. Line 170, you set current node to root node. So this might be bringing some memories back from last lecture where we saw that you start from the root of the tree and then you keep going down until you hit a leaf and you decode that leaf and so on, right? So all of this is implemented and you will use it in your homework, and you can read it if you don't understand something in the lecture, because often for many of us, reading a code helps us bring more clarity than just a sort of a vaguely drawn diagram in the lecture. So there will be a tutorial on SCL which will help you get started, which will be posted later this week sometime. So that should be very useful for you as you start your homework. And again, if you're struggling with anything that seems to you that it's our fault or it's SCL's fault, talk to us. We will help you out. Any questions on this? Yeah, I'm sure you will have questions once you get started. But for now, let's move on. Okay. So last time's quiz, we will come back in a bit. Please be patient. I want to cover one topic which will be useful to talk about the quiz. Okay, so last time we talked about prefix codes. So prefix codes are codes where no code word is a prefix of another code word, and we saw that it really simplifies the decoding. And one way of decoding was this tree-based thing where you start from the root, you go down the tree and so on. Right, I've drawn one of those here where if you see a 1, 0, you go this way, then you go this way, and you decode a B, and then you go back to the root, and then you see like a 1, 1, 1. So you go to D, you decode D, you go back to the root. I won't spend too much time. I think you might have gotten some practice in the homework, in the quiz. Then we defined a good code. I just gave you a thumb rule, asked you to believe. We will show this time why this held, but we said that a good code has the length of a symbol, the length of the encoding of a symbol is roughly the log of 1 over px. And then we actually constructed a code called the Shannon code, where the lengths were actually very close to the promised good code. For Shannon code, we did the construction. Construction was very simple. We sorted the symbols according to their length, and then we just basically pick a code word that doesn't violate the prefix precondition. And I think you had some homework questions on that. Then we did the proof for why that construction works. Even if you didn't fully follow the proof, that's totally fine. We won't be using that. You will see a proof which is very similar, so hopefully that helps better understanding. Okay, so first topic today is Kraft's inequality. What is Kraft's inequality? So last time we saw that a prefix code is equivalent to having your code words be leaves on a binary tree, right? But so when we say prefix code, we mean no code word is a prefix of another, leaves of a binary tree. These are very sort of English sort of representations of the thing, not as mathematical as some of you might like. Today we will see a characterization of prefix codes which is very mathematical. You can see a prefix code is equivalent to satisfying a certain inequality, which we'll just see in the next slide. And this will be very useful for the rest of the lecture and beyond. So this is the inequality. So first part is the forward part, and then we have a converse. So given a prefix code with certain code word lengths. Oh, by the way, these will be posted on the website. So yeah, if you want to take notes, but if you don't, then that's fine. Okay. So for any prefix code in the world that has certain code word lengths L1 to Lk, the sum of this quantity, summation I equal to 1 to k, 2 to the minus Li, is less than equal to 1. Right? And we'll see this come up again and again. So for now, okay, this is something. And maybe the converse part might interest some people more, which is that given any set of integers L1 to Lk, satisfying this inequality, there exists a prefix code with lengths L1 to Lk, right? So basically having a prefix code is equivalent to satisfying Kraft's inequality on the lengths. So it's an if and only if sort of situation. Any questions before I move on? We'll see some examples in a second. Okay. And don't worry if it looks very abstract, like why are we doing this? We will, as we move on, I think by the end of this lecture, we will have a very strong intuition about some of this. My ink ran out here. Okay. Proof of the converse part. So converse part says that if you have a sequence of lengths satisfying this inequality, then you can create a prefix code. This I won't cover too much. Basically, it's the same construction as Shannon codes. So you sort the lengths, you pick lengths, you pick a code word according to the prefix condition, and you get a code at the end. Right. So let me not do an example. I think it's the exact same construction as the Shannon codes. Yeah, feel free to revisit. Okay. Okay, the forward part, I will do a proof sketch, which should give you enough intuition, and maybe it will help you understand the proof from last lecture better as well. So what do we need to prove? We want to prove that if you have a code, prefix code with these lengths, with lengths L1 to Lk, then this inequality holds, this one, summation I1 to k, 2 to the minus Li less than equal to 1. So this is what you need to prove for any prefix code in the world. So how will we prove it? We define something called Lmax. Lmax is the maximum. Lmax is the maximum length, maximum code word length, basically the longest code word. Okay. So this time I came prepared with a diagram. So, okay, so let's see what what we can. So I've drawn here the actual code, all the code words on a tree, and I've shown the depths of the different leaves. So L1, L2, L3 are at the same depth. L4 is the deepest node in the tree, which is same as L max, because that's the deepest one, right? Now, this is something I think we saw last lecture, that 2 power L max minus Li is the number of descendants of the ith code word at depth L max, right? So we saw this last time. I won't dwell on it too much. Basically, the idea is if you have a binary tree of depth n, then the number of leaves is 2 to the n, right? So if you are at depth Li already, and then you need to go to depth L max, so the binary tree starting at Li up to L max has number of leaves 2 to the power, like the difference in the heights. So let me illustrate it here. Like if you see at this part, right? So this is L1, this is the node L1, and this is the sort of sub-tree that you can like create, which is the children of this guy. And this has number of nodes, which is like 2 to the L max minus L1, number of leaves. And so on for this guy, so on for this guy, and so on. Okay. The other property we will use is that if we have node I and node J, their descendants cannot overlap. Why can't they overlap? Because prefix free property, right? So you can see it, and sometimes it's easier to see in the picture, right? Like clearly these guys can't overlap because they are just like separate branches of the tree. So therefore, if you add all of these up, you add all of these guys who are at depth L max, their sum will be lower than the total size of the number of nodes at depth L max. So this, like we are using a very like simple property where like if you have a bunch of disjoint subsets and you add up their sizes, that cannot be more than the total size of the entire set, right? So summation of this thing is less than equal to L2 to the L max. Yeah, let me give you a minute to absorb this, and if you have any questions, please ask.
Li and through all of these, they're like the number of branches before you get to the leaf.
Yeah. So it's sort of yeah, that's one. Like it's the depth or it's the length of the code word. That's the way to think. Yeah. So like L1 is like 1 because this is 1, right? L2 in this example is 3 because there are like 3 things. Yeah. I think this is the last time you will see this tree style proof. So if you don't like it, this is the end. Okay, let me move on. Okay, we'll go to the quiz. Before that, let me just say that last lecture, if you remember, we talked about prefix codes, but we also talked about a bigger category of codes called uniquely decodable codes, which were like basically lossless codes. And here, as you see, we are proving Crafts inequality for prefix codes. In the homework, you will prove Crafts inequality for uniquely decodable codes, which is just a more powerful statements because prefix codes are a subset of uniquely decodable codes. So, and that's a very different proof style. So I hope you enjoy that one as well. Okay, let's do the quiz questions, and here we will do some examples of Crafts inequality as well. So this will help you get familiar with the thing. Okay, I think here I will ask for your help. So here the question was, you were given a distribution over A, B, C, D, E, and you wanted to build a Shannon code for this distribution. So you could just use that Shannon code construction algorithm. So can somebody help me with, I already like computed the lengths of the code words with this formula, right? So now you only need to tell me the code words with these lengths. Please, anybody? A. Okay, someone says 0, 0. Yeah, so the algorithm is like you just pick any available code word at that length, right? And available means that it shouldn't be a suffix or prefix of anybody else. Okay. B. Okay, I hear 0, 1 and 1, 0. Let's choose 0, 1. Keep it simple this time. Okay. C. Okay, I see 1, 0, 1, 1. Let me again take 1, 0. So easier, more lexicographic. Okay, D. Okay, D, let's do 1, 1, 0, right? So we could, for example, we couldn't choose 1, 0, 0 because that would be like C would be, then it would violate the prefix free property. But 1, 1, 0 is totally fine. E. Yeah, so E, you see, you could have chosen 1, 1, 1 in a good code, but a Shannon code must have these lengths. So it's like suboptimal in that way. So we have to choose a code word with length 4. So let's choose 1, 1, 1, 0, which will satisfy all the prefix properties. Okay. And the expected length, that was question 2. I hope this is very easy now. So you just do the math, you get the 2.37. Okay. Okay, this is something that should have been on the quiz, but we couldn't add because I didn't finish on time. We just saw that Kraft inequality, right? 2 power minus Li, the sum should be less than equal to 1. So if we compute that sum for these lengths, you can do the math. You get 15 by 16, which is less than 1. So that's good. You are satisfying the Kraft's inequality. And there is a gap actually, like it's not equal to 1 here. And we'll come back to that gap in a second. Right. I hope this is very clear. So 2 power minus Li, you are summing over. So 2 power minus 2 plus 2 power minus 2 plus 2 power minus 2 plus 2 power minus 3 plus 2 power minus 4. That's the math here. And the total is 15 by 16, which is less than 1. Any prefix code will always satisfy the Kraft's inequality. Okay. Then we asked for a better code, and I already made it at home. So as some of you, I think, suggested that the last length need not be 4, right? This is clearly suboptimal. You could have chosen length 3 here. Is that clear to everyone? That you could have chosen length 3 here, right? Because 110 is also not a prefix or suffix of anything. Okay. Now if you compute the expected length, you actually get 2.25, which is strictly lower than the 2.37 we got for the Shannon code, right? So Shannon code is a good code, but it's not the optimal code. In this case, it can be better than the Shannon code. And in fact, if you now compute the Kraft sum, right, that 1 over 2 to the L and you sum it over, you actually get 1, right? So you will see in the next lecture that an optimal code satisfies Kraft's inequality with equality. So for an optimal code, the summation of 2 power minus Li is actually equal to 1. So actually the gap between 1 and your Kraft sum tells you how far you are from the optimality. Okay, any questions on question 1? I think most of you got it right from what I remember. Okay, good. Second was, I think, very easy. I hope let's quickly solve it together. We just asked, are these codes prefix free? Was 2.1 prefix free? 2.1, some people are saying no, and I think it is not, right? Because see, D is a prefix of E, so clearly no. Okay. I hope that's clear. Okay, let's compute the Kraft sum for this guy. So it's like you have 4 terms which are like 1 by 2 square, because you have 4 things which have length 2, and then you have 1 term which has length 3, right? So this is just 2 power minus Li. I'm summing over all the code words. And if you do the math, this will be more than, it's like 1 plus 1 by 8. So it's greater than 1, right? So we saw that any prefix code has to satisfy Kraft's inequality. So if your code doesn't satisfy Kraft's inequality, it cannot be a prefix code, right? So another way to check. Okay, just by looking at the lengths, you don't even need to see the code words. Just by looking at the lengths, you know that it's not a prefix code. It cannot be a prefix code. Okay. Is that clear? That the Kraft's inequality basically gives you a way to identify prefix codes. Okay. 2.2. So you have these 5. Was this a prefix code? Okay, people are nodding. Good. Yes, it was a very easy to check again. And if you compute the Kraft sum, which I think it's 5 by 8. So this is less than equal to 1. So good. It satisfies the Kraft inequality. Great. How about 2.3? Is that a prefix code? Yeah, people are saying no. And they are correct because these two have the same. So it's a very bad code. Okay. Now if you compute the Kraft sum for this guy, it's like 3 divided by 4 plus 2 divided by 8, which is like 1. So how is this possible, right? So this satisfies Kraft's inequality. The sum is like less than equal to 1. But it's not a prefix code. Can you square that with like the results we just saw?
I could just switch.
I think you're on the right track. Like Kraft's inequality, what it says is that if your lengths satisfy the Kraft's inequality, then you can, then a prefix code exists, right? But your particular code need not be a prefix code. You could just make a code where everything is 0. So clearly it's not a prefix code. But you could make a code out of just by slight modification of this, just make it 0, 1, and then it becomes a prefix code, right? So if Kraft's inequality is satisfied, you will get a prefix code. But your particular code may not be that prefix code, right? It could not, like, it might just be not a prefix code. Okay, are people good with that? Okay, good. Okay, let's move on. The exciting parts. So what will we do? We will talk about some information theoretic quantities. If you do an information theory course, you will see much more on these. We will just do enough for compression basically. We will very precisely characterize what is the best prefix code. As we saw, Shannon code is clearly not the best prefix code, but it's a good one. Okay, and then we'll justify the thumb rule, which is that the length should be roughly log 1 by px, right? This log 1 by px will keep coming again and again throughout the course. And if you have done machine learning, you will see that it even comes up there where you have these log loss terms, and you have, there was a recent paper by DeepMind, the Google subsidiary, where the paper is just called Language Modeling is Compression. And we'll see that in the later homeworks and so on. Like there's a very deep connection between compression and modeling or learning in general. But yeah, just this basic thing we'll just keep talking about it. Okay, so first quantity, entropy. How many of you have heard about entropy? How many of have heard about entropy in a physics context? Yeah, so see, many people are familiar about entropy from physics context, right? Where I've not done physics, so I don't know what it exactly means. So I will tell you what it means here, right? So I think it's very similar conceptually. Okay, so you have a alphabet 1 to k. From now on, we will not talk about A, B, C, D. It's just harder to keep track of. Our alphabets will typically be just 1, 2, 3, 4, k. You have a probability distribution over that, and we will use this shorthand notation. Pi will be the probability that x is equal to I, just to simplify our notation. Then entropy is this quantity. Sum of Pi log 1 by Pi. The unit of entropy is bits. We will see why in a bit. Okay. We'll do some examples and then I will wait for questions. So one thing you notice is that entropy only depends on the probability distribution. So entropy is really not a function of x. It's not a function of the random variable. It's a function of the distribution. If you have two random variables with the same distribution, they have the same entropy. It's a function of the distribution. You can write the entropy as an expectation, right? Because you see here that like you remember that the expectation is like expectation of some y is like summation pi y xi, something like this. So this. Okay, so here like it's just pi times log 1 over p x equal to I. That's just by the definition of expectation, right? So it's just a easier way to write it. And third thing, like if you have actual questions on this, like if you ever run into a place where you want to compute the entropy, or if you want to write it in Python, right? Like a code to compute entropy. When p is 0, this term is 0. You can either assume it or you can like you use your calculus, take the limit or whatever you want to do, but this is 0, right? Otherwise you run into like not a numbers and ifs and so on in your Python script. So that's just like a definition. Okay. Any questions so far? We'll do some examples now. Okay, let's do examples. So you have a uniform distribution. So your x is uniform x is uniform over 1 to k. Right. So what that means is like px equal to I is just 1 over k for all I. Then your entropy of x is, just use the formula from last slide, right? So p log 1 over p, that's the formula. And after you like do the math, you see log k. Bits. Okay. Is that clear? Good. Have you seen log k in any other context for uniform distributions in the past? In the last like 2 lectures basically. Let me just remind you, you might remember that log k is actually the length of the fixed length code for, or I guess the ceiling of log k, right? So you already see that there is some connection between entropy and the length of a code, and we will explore that shortly. Right. So in particular, if x is like Bernoulli half, right? So Bernoulli random variables, this just means that uniform over 0 and 1. Then h of x is log 2, which is 1 bit. So if you have a random variable which is either 0 or 1 with equiprobability, then it has 1 bit of entropy. Right. Okay. Let's just compute it for this one also, just so we are very comfortable with the calculations. So half log 1 over, you will have some questions in the homework, in the quiz and the homework. Times 2, so this is like half log 1 plus 1/4 log 2 plus 1/8 times 3 plus 1/8 times 3. So half plus 6/8. Seven by 4 according to helpful audience members. Okay. So as a sort of exercise, which I would encourage you to do at home, if you have this code, if you create this code for this distribution, then if you calculate the expected length of the code words, yeah, just compute it at home and you will find that it's the entropy. So again, you see some connection between the length, average length of the code words and the entropy. Okay, any questions about, for now you should just know that given a distribution, you follow this exact formula and you know the entropy. That's it. And we'll see more shortly. Properties of entropy. So for a random variable that takes up to k values, the entropy is between 0 and log k. We already saw when it's log k. It's log k when it's a uniformly distributed. And it is 0 when it is deterministic. By deterministic, we mean that x takes exactly one value with probability 1. So it's not random, it's deterministic. So again, for a random variable that takes values in an alphabet of size k, entropy is between 0 and log k. I won't do the proofs. The 0 proof is very easy. It just depends on the fact that probabilities are less than 1. And the log k proof uses convexity and Jensen's inequality. So for those of you who are familiar with that, it's a few lines of math. Okay, so let's just talk about what entropy means and so on, right? So entropy is it's like a measure of uncertainty or randomness in your random variable. So if your random variable is deterministic, there is no randomness, entropy is 0, right? If your random variable is uniform over all possibilities, then it has the maximum entropy, right? So the more random your thing is, the more entropy it will have, right? So that's just what it means. Very similar meaning in physics, I believe. Another way to think about it is the entropy is the amount of information contained in a message. So for example, let's say you have a friend who sends you messages, and all the messages they send you are hello. They just send the same message every time. So when you receive the message, it gives you very little information, right? Some other person, somebody, sometimes they say hello, sometimes they say hi. So maybe you have some information, right? So the more entropy you have, the more variability you have, more information you can capture in that message. So entropy is the amount of information that's contained in a random variable. A deterministic random variable has 0 information. And since at the end of the day, compression is about storing the information, entropy is also how much you can compress, and this we'll see in this class, that entropy is the limit of compression. For a given random variable, the entropy is the best compression you can achieve for that random variable. And that's why the unit is bits. And if you have ever seen these sorts of puzzles, I have X coins and then one of the coin is lighter than the other coins and one of the coins is heavier, and I have a weighing scale and I want to how many minimum number of weighings should I do to get find out the heavier coin or the lighter coin. Or you have a bunch of contestants in a tournament and then one of the contestants is stronger, everybody else is equal. How many tournament rounds do I need? So there are a bunch of these puzzles, and many times you will see the answer is related to entropy. And you will see some of those in our homeworks. Entropy is also important for sampling from distributions. So you have a fair coin, but you want to simulate a biased coin, or you have a biased coin and you want to simulate a fair coin. All these situations, entropy comes up as the limit of things. I think we will see all of these to some extent in the homeworks, so I won't spend class time